In an effort to prevent expensive shutdowns and unplanned maintenance downtimes, facilities across the globe today rely on a variety of preventive maintenance methods. Many studies indicate that temperature rise, otherwise known as hotspots, is a major cause for these failures. These abnormalities are often caused by loose connections as a result of vibrations, unbalanced loads, overloaded conditions, and a wide range of other issues often found in conductive environments. Most industries use either routine physical inspections or thermography programs to detect temperature abnormalities. Physical inspections require the user to open the electrical enclosure, barriers, and other insulating materials in order to inspect the connections. Since most facilities prohibit their personnel from this type of high-risk access, the data obtained is often inaccurate or unobtainable. Additional risk of failure exists when the equipment is not put back in the original condition after inspections. To overcome these shortfalls and to measure the temperature of the live conductors, some facilities use infrared cameras and windows. With this method, an IR camera is directed at a live conductor either directly or through an IR window to measure the rise in temperature. In some cases, the IR camera or the window visibility is restricted by the connection location and field of view of the IR window. To help you address these concerns effectively, we'd like to introduce our new GraceSense Hotspot Monitor, or HSM, a continuous real-time temperature monitoring device intended for locations that are difficult and hazardous to access. This device not only measures the temperature at any given point in time, but also proactively monitors and enables the user to predict the failure before a potential shutdown. The HSM utilizes patented fiber optic technology, providing constant temperature data available in 9 or 18 independent sources. The fiber probes can be mounted onto electrical bus bars, bus ducts, transformers, or any other source of heat. The Hotspot Monitor provides a unique combination of patented fiber technology and advanced algorithms that convert the change in light intensity to temperature. The patented fiber probes securely connect to a ring-style connector that conveniently mounts to the source of heat, while the other end connects to the HSM module. Sources of heat may include inaccessible equipment and blind spots to IR scanning. The most obvious benefits of the HSM over IR thermography come from the continuous real-time monitoring feature. In addition, the successfully proven measurement accuracy of the probes is not subject to calibration errors, as can be the case with IR scans. The Hotspot Monitor comes with 16 megabytes of built-in memory for data storage. By connecting the GraceSense HSM module via Modbus TCP/IP or Ethernet IP and accessing the web utility tool, users can configure the temperature thresholds, time intervals, and relay outputs. This tool further enables access to the real-time data logs and downloads the stored data for analysis and trending, connecting directly to the device or safely through closed doors using a GracePort Ethernet connector interface. GraceSense Hotspot Monitor is a reliable and affordable solution for use in environments with low, medium, or high voltage systems. The HSM is available in 2 versions, either a 9-point module with a built-in LCD display or an 18-point module. The unit comes fully kitted with fiber probes, ring-style connectors, and an installation kit. Optional accessories include a Modbus current sensor, high-temperature probes, ambient measurement attachment, custom connectors, and fiber lengths of various sizes. Continuous real-time monitoring, our answer to your most demanding and critical applications where guesswork and downtime is not an option. To learn more about our Hotspot Monitor, visit gracesense.com or call 800-280-9517. Find faults before they find you.
Good morning, everyone. Thank you for showing up today and dialing in and listening to this presentation. Or good afternoon if this is the afternoon session. My name is Jay Prigmore. I am a managing engineer at a consulting company called Exponent. And I'm in the electrical engineering computer science practice. And I perform quite a bit of arc flash studies, and I'm actually on the IEEE 1584 working group and was a voting member on this standard. So today basically the topic is going to be, what changes occurred between the 2002 edition and the recently released 2018 edition. There was a substantial difference, although the end result is similar. But there's a lot of different things that occurred and different equations and the number of factors that have changed based on improved data and test data. So I'd like to welcome everyone here, and I guess let's get started. So I wanted to kind of, before we get into the presentation, give a few takeaways or some high-level overviews and some thoughts to really emphasize as we go through this presentation. The first one is that the standard has changed significantly from the 2002 edition to the present 2018 edition. While the outputs may be very similar, the inputs have changed, and a lot of the intermediate steps have also changed, including the equations. And the equations are much more complex and accurate than they were prior because of the more test data. There's been a lot of extra additional tests, and the equations were refined based on this empirical test data and also a statistical analysis that was performed. Additional information for each equipment model or each piece of equipment may also need to be gathered that is, like I said, addition from what was done in 2002. And examples of that are the electrode configurations as well as like enclosure sizes. And there's correction factors that need to be taken into account when performing the arc flash analysis. So before we get into the background and some of the meat of this presentation, first thing I wanted to cover was the purpose of IEEE 1584. And they have a purpose statement in the document that basically says word for word on the slide that it is to enable qualified persons or person to analyze power systems for the purpose of calculating the instant energy to which employees or workers could be exposed during operations or maintenance work on electrical equipment, particularly energized electrical equipment. So contractors and facility owners can use this information to provide appropriate protection for employees. So what this means is they basically take the results of the arc flash analysis, and you can then reference other standards such as NFPA 70E and determine what the appropriate level of personal protective equipment or PPE is for someone performing energized work while doing maintenance or operations work on electrical equipment. So now that we know the purpose, the next is to get a little bit of a background or a history lesson on IEEE 1584 and see kind of where the standard has developed over time and what changes have occurred and why things were done the way they were done and why the new equations have been adapted and why they're a lot more complicated than the original 2002 edition. So IEEE 1584 basically provides a model and an analytical process that enables the calculation of what's a predicted incident thermal energy and the arc flash boundary. Basically what this means is it allows you to calculate the type of energy at a specific distance away from the energized equipment should an arc or electrical arc occur. And it also provides arc flash boundaries of where a worker or a maintenance personnel or whoever is doing the work needs to rope off the area and secure the area so that any non-qualified person doesn't encroach into the arc flash boundary, especially not wearing PPE, and minimizes any sort of damage to that non-qualified person. It also provides guidance on based on the instant energy levels. One can use like NFPA 70E or other sources to determine personal protective equipment requirements for the person at that panel or wherever they're doing work at to properly protect themselves based on these calculations. It does cover the collection of field data if applicable, and field data, whether it's collected by the engineer or not, or whoever's running the study or not, the field data needs to be verified at some point, and if not, then one of the main assumptions you should put in is that field verification was not part of your arc flash study. So you assume that the drawings that were provided were true and accurate, and if they're not, then it might invalidate the incident energy analysis or the arc flash analysis. One thing that's also needs to be discussed is the number of operating scenarios and which operating scenarios are likely to be investigated. The ideal situation is you'd like to get all the operating scenarios, but there's going to need to be some input from the client on which operating scenarios they operate in. Might be just a couple, like a normal and a main. Normal and an emergency, or it might be one source on, one source off, or both sources on, depending on how it's all configured. And then it also covers the parameters necessary to perform these calculations, and we'll get into that in a little bit. But the application of this includes electrical equipment and conductors for three-phase alternating current or AC voltages from 208 volts up to 15,000 volts or 15 kV. That's the bounds of this standard. So some things that IEEE 1584 does not cover is single-phase systems. Presently the standard is strictly three-phase systems. However, there are discussions and there has been some test protocols and test plans developed for single-phase systems while we're in the working group meetings. They haven't been performed yet, and they haven't actually been included in the standard. Doesn't mean that they're not going to be included in a future revision. But at the moment, the only guidance really on calculating the incident energy from single-phase systems that's presented in IEEE 1584 would be to use the three-phase equations, and basically the results of the three-phase equations are expected and anticipated to be conservative estimates and not, more appropriate or more accurate estimates for single-phase systems in particular. However, that conservative estimate, may require someone to wear a higher rated PPE or safety equipment than what would necessarily be needed if it was an actual single-phase calculation. 1584 also does not cover direct current systems or DC systems, but it does provide a number of reference publications for anyone who's looking into doing a DC arc flash study. And it also does not provide personal protective equipment recommendations either, or PPE requirements or PPE recommendations. You have to go to a different standard such as NFPA 70E to find those PPE recommendations based off of these incident energy calculations. So a little more background on IEEE 1584, especially on the testing and the tests that were done to calculate these or determine these empirical equations used in the calculations. The 2002 edition was based on over 300 arc flash tests, and that was basically came from about $75,000 in funding from various sources. And these tests utilized a 20-inch or 20 cubic inch box or an enclosure. The 2018 edition, however, ran an additional 1,700 arc flash tests. So the equations and the empirical data derived in 2018 is approximately 2,000 arc flash tests. So the 300 prior plus the 1,700. And the working group committee was able to secure about $3.5 million in funding to perform these tests, although the desired amount was about $6.5 million. So it fell relatively short of the requested amount, but still enough to perform all these tests. One thing to point out is the modeling is much more complex compared to the 2002 edition, and one of the reasons why is there's, in the 2018 edition, different types of electrode configurations and enclosure sizes were taken into account, along with various voltage levels and various current levels and a number of variability in the test. Kind of a overview of which tests were performed in the 1,700 test, or approximately 1,700 tests, is shown in the table on the right. So we had about almost 200 tests at the 208 three-phase or 240 volt single-phase test voltage. Had about 400 tests at the 480 volt system voltage, 340 tests at 600 volt system voltage, 320 tests at 2.7 kV, about 200 tests at 4160, and about 270 tests at 14.3 kV. So this is kind of the test voltages that were performed in the 2008 edition. And then a lot of this, based on this data, they were able to determine a empirical equation that you could then, based on your own system voltage, you could then apply a correction factor and then calculate the incident energy at your particular system voltage versus, you know, these 6 voltages listed here, or 7 voltages listed in this table. So in comparing the 2002 edition and 2018 edition standards with each other as far as what's required and what are some of your inputs and what are some exceptions, the 2002 edition basically was broken down into 2 separate branches. The first branch, or the path they put you on, was if the system voltage was 1,000 volts or less than 1,000 volts, you would go down branch A, which would then take you through certain equations and you'd make some calculations. The second branch was if the system voltage was between 1,000 volts and 15 kV, then you would go down the second branch and then find your results. You would then calculate the incident energy based on whichever branch you were on, and then you would then calculate the arc flash boundary. 2002 also introduced the 85% rule. Well, I believe that was a 2004 amendment that was included in 2002. But the 85% rule basically says once you calculate your arcing current and you have your incident energy and arc flash boundary, you need to recalculate the incident energy and arc flash boundary with an 85% arcing current from what was originally calculated. The reason being for that is that if you're right at the border on some settings, some protection settings, by dropping the arcing current by about 15%, you know, a fixed 15% to down to 85%, you can see if you would then transition, say, from an instantaneous setting that would pick up the arcing fault to a short time, or from a short time to a long time. And that extra duration that's added based on the 85% rule could be significant when it comes to the overall available incident energy at that location. 2002 also had a 125 kVA transformer rule exception, where if you had a 125 kVA transformer, or something that was less than 125 kVA transformer that was providing equipment from an upstream position, then you could eliminate or not even perform the arc flash analysis for that downstream equipment that's connected to the 125 kVA transformer. 2002 also introduced the 2-second rule, which basically says that based on the configuration of the equipment and the enclosures and where the person's going to stand, if it's feasible, or an engineering decision is made that it's feasible for a person to remove themselves away from the hazard or an arc flash within 2 seconds, then the incident energy calculation can be cut off at 2 seconds, even if the circuit breaker or fuse or whatever the protective device is, you know, wouldn't operate for an hour or 5 hours or a week from the actual incident of the arc flash due to its installed protection settings. However, this one caveat there is that, you know, the engineering decision needs to understand, can somebody reasonably get away from the arc flash? Are they inside a vault where they climb out? Are they in an open area where they can just easily run away? Are they in an enclosed area or a crowded area where there's just equipment around them and they might be pushed back or might be trapped up against a piece of equipment and they actually can't, you know, remove themselves from the situation? So I advise everyone who's doing the arc flash and who actually uses the 2-second rule to, you know, be careful and understand some of the limitations of that 2-second rule. In 2018, some of the variables that are needed are, you know, listed here, such as the electrode configuration, the open circuit voltage, bolted fault current, working distance, the arc duration, which is the protective device operating time, pretty much, you know, and some switching contact time, or some switching time if there's an actual switch that actually operates, the conductor gap, as well as enclosure size. And a lot of the enclosure sizes listed in the standard are the typical NEMA size enclosures and typical gap distances for the voltage ratings. The 2018 edition removed the 85% rule and actually replaced it with the minimum arcing current equation. So it's no longer a fixed 85%. Based on the system information and the configuration, there's now a minimum arcing current equation that's needed to calculate, that then gets put through the same rigor as the 85% current used to. There's the 125 kVA transformer rule was also, or that exception was also eliminated from the 2018 edition. But the 2-second rule stayed, and it's actually in section 6.9.1. So now that we've kind of touched on the background a little bit, let's go into some of the meat of the presentation and kind of the major changes and what those implications are from the 2002 to 2018 edition. So the 2018 edition introduces a major change, which is like a 2-step calculation process. The first step being the intermediate calculations, and the second step being the final calculations. Each of the intermediate calculations require a three equation calculation that takes into account some of the electrode configuration and some of the coefficients that are found up in tables regarding to the certain voltage levels. And then the final calculation takes into account also some other correction factors that are used, after applying to the intermediate values for like enclosure box size and then arc current variation. Basically, you calculate the arcing current at the 3 fixed voltages, and then you interpolate and use a correction equation and correction factor to basically interpolate to your actual system voltage. So say you calculate it at 600 volts, you would need to get that 600 volt result and interpolate it down to your 480 volt system. And this is done at intermediate values of average arc current, the incident energy, and the arc flash boundary. So another major change that occurred in the 2018 edition is basically the improved accuracy of the model, and that's based off of the approximate 1,700 additional tests that were performed between 2002 and 2018, plus the 300 original, for a total of about 2,000 test points that form the basis of these newly defined or newly derived empirical equations that have then since been updated from 2002 to 2018 edition of the standard. Also, the improved model, like the equations, they take into account additional factors that weren't in 2002 edition, such as the additional electrode configurations, such as the enclosure sizes and having correction factors for that, and also that the voltage spectrum is now a continuous voltage spectrum versus just fixed set points. So whatever your voltage is, you can have a correction factor that'll more accurately, or that improved accuracy will calculate the incident energy that's most appropriate for that voltage level. So speaking of the voltage spectrum and some of the other additions in the model, or changes in the model range has actually increased, and you can see from these two different columns, the red highlighting, or the red text on the slide, show a lot of the changes that occurred versus what happened prior in the 2002 edition. So in 2002, the model was applicable from 208 volts to 15 kV 3-phase, again 50-60 hertz, and the voltage fault current was from 700 amps to 106,000 amps. And they also had equipment enclosures were commonly available sizes, and the gaps between conductors were set between 13 millimeters and 152 millimeters. In 2018, you still had that same 208 volt to 15 kV 3-phase voltages. You still had the same frequencies, but your voltage fault currents and the RMS symmetrical voltage faults have changed. So instead of being from 700 to 106 K, throughout that whole spectrum, as you can see here, from 208 volts to 600 volts is actually from 500 amps to 106 K, and yet from 601 volts to 15 kV, it goes as little as 200 amps to about 65 K. So So that's a substantial difference. And the gaps between the conductors has also changed. So you can kind of see the different ranges based on the red text there between 208 and 600, and then 601 and 15 kV as compared to the 2002 edition. The working distances, again, are greater than or equal to 305 millimeters, so 12 inches, greater than 12 inches. And the fault clearing time didn't have a limit in 2018, and then we've also added the electrode configurations and the enclosure dimension limits, in this model. As I stated earlier, the 2002 edition had basically two equations that were based on, two voltage ranges. One was less than 1,000 volts, the other one was between 1,000 volts and 15 kV. In 2018, there's three equations for three voltage ranges, for like the intermediate equations. And those ranges are 600 volts, 2.7 kV, and 15 kV. And then you need to calculate each of these equations, because in the final values, these, or the minimum currents, these equations are needed in that next step process. And then there's some guidance based on whatever voltage you have on which of those final equations you use as your final arcing current. And like I said earlier, the final results require interpolation to scale to the actual system voltage if it differs from these three voltage ranges. So next, one of the major changes and actual additions is the electrode configuration. In 2018, there's 5 different electrode configurations that were tested. It's also known as Table 9 in IEEE 1584 2018. And these 5 electrode configurations, the first one is VCB, which is vertical conductors or electrodes inside a metal box or enclosure. And VCB was included in the 2002 edition. VCBB is vertical conductors, electrodes terminated in an insulating barrier inside a metal box and enclosure, which is new. HCB, which is also new, is horizontal conductors, electrodes inside a metal box or an enclosure. VOA, which was included in 2002, is vertical conductors in open air. So VOA, vertical open air, and like I said, it was in 2002. And then HOA, which is new, is same as VOA, but it's horizontal conductors in open air, and that was added in 2018. And some pictorial representations of these conductors are shown below, with what basically they stand for: VCB, VCBB, HCB, VOA, and HOA. It kind of shows you in the bottom of pictorially what each of those configurations look like. And these photographs were taken directly from IEEE 1584, so you can actually find these photographs in the standard itself. So we just saw the pictorial diagrams that are presented, or the cartoon diagrams that are presented in IEEE 1584. But what do these installations really look like in the field? If you look at the top left photograph, that is a VCB installation, and it's highlighted by the red circle. So that's the load side of a circuit breaker, where the cables terminate into it on the bottom side, and there's no barrier right at that connection point. In the bottom left photograph, there's the VCBB installation, which is the same circuit breaker, but the cables are now terminating into the top side of the breaker, or the line side of the breaker. And because of the breakers there itself, the breaker itself provides a barrier, so that would be a VCBB installation. The middle photograph is an example of an HCB installation, because you have the conductors coming out facing toward the person they're standing right next to it. And that's shown in the red dotted circle as well. And the upper right photograph is the VOA installation, which is the vertical open air. And you can see these conductors are installed vertically, and they're not in an enclosure, so it's open air. And in the bottom right photograph, there is the HOA installation, which basically shows horizontal open air. So these could be stabs or connection pads from a transformer, or some other device like a circuit breaker potentially that actually has the conductors facing or pointing toward the individual standing next to it. And just want to mention that each of these photographs were taken directly from the IEEE 1584 2018 edition, and they actually are included in the standard. So if you wanted to go see some of the commentary on these photographs, please refer to that standard. So here's an example of an installation that could have multiple electrode configurations, where you would need to calculate the arcing current and the incident energy based on these different electrode configurations. So here showing is this VCB or is this HCB? If you look at the blue circled area where the blue line's pointing, or the blue arrow's pointing to, VCB shown because it's a vertical conductor that's not going into it's not open air and it's not going into a barrier. So it's a VCB installation, while it also has an HCB installation because of these stabs that the device connects into, and that's a pretty large difference between the two. So just want to say that a couple different electrode configurations could change based on actually how it's installed. So that's very important information to gather when performing these arc flash studies. Here's another example of a single installation that may have multiple different types of electrode configurations, which then again makes things a little more confusing. The photograph on the left shows a VCB configuration, and it's basically the load conductors exiting the circuit breaker. The middle photograph is a VCBB electrode configuration, as the conductors or the cables enter the top of the breaker, and you have that top of that breaker as an insulating barrier. And then if you look on the right photograph, there's the screws, or the screw terminals that you can actually screw at the connection points. You can screw in the cables that connect to the bottom of the breaker, and because those screws are live and exposed, they're actually touching the live energized cable. So that would also be an HCB configuration. So again, which one do you choose? And the best way is to choose all three and calculate for all three, which is why the use of commercial software is very beneficial and very helpful in this sense to speed up some of these arc flash studies, because that's a number of calculations you can do at thousands of different points in the system. Because each of these electrode configurations or each installation may have multiple types of electrode configurations in a single panel or a single enclosure, the question may become next is, well, which one's worst case? And if I don't do one, am I underestimating the incident energy? Or if I do one, am I overestimating the incident energy? Or we can actually have a much lower value, so that the person may not have to wear a category 3 or 4 PPE requirements, and maybe only category 1 or 2. So IEEE looked at it, and here's a plot of different configurations along with VCB and VOA, and then a lot of the new values that were occurring. The dotted lines in this were from the 2002 equations, or the test, while the other lines, the non-dotted lines, are from the new 2018. And if you look, the largest or the most severe would be the HCB, so it would be the horizontal conductors in a box. That is the red line on the top, followed by VCBB and HOA, or horizontal open air. So those are your most severe, and then you go by, then the dotted line is the VCB, and the new VCB is the blue line. And as you go down farther and farther, you also have the vertical open air. So the vertical open air is probably the least severe based on this graph, followed by the VCB is the next least severe. And the one that's really important is if there is a HCB configuration, that's something you definitely want to look at and include in your arc flash study, because that could significantly change the incident energy calculations as shown by this plot. So one of the other additional major changes was the equipment class, or the enclosure size. These two different tables here are both actually produced in the 2018 edition of IEEE 1584, but as you can tell from their titles, one is relevant from the 2002 edition, and the other one is the 2018 edition. And the 2018 edition has a number of additional enclosures and enclosure sizes. So I just wanted to point out that a lot of additional enclosure sizes were taken into account when performing these 1,700 additional tests. And because of that, you know, these equations are, the empirical data suggests that they're much more accurate than what occurred in the 2002 edition. And this actually shows you like the different default bus gaps and enclosure sizes based on what type of equipment class there is. So this is useful information when performing your updated 2018 edition arc flash study. So in summary, the equations have become much more complex than they were in the 2002 edition. Calculations, you know, each of these equations, you need to perform calculations at 3 different voltage levels: 600 volts, 2.7 kV, 14.3 kV, and then you interpolate to your actual system voltage, both in intermediate and you got to do it, you know, in final. Coefficients that are provided in these more complex equations, or these longer equations, are provided in lookup tables for use in the 3 voltage level equations and are based on the actual test data. So they were empirically derived and statistically derived based on the test data. If you use a commercial software to do this, a lot of the commercial software programs have these coefficients based on your voltage settings already pre-programmed. So, you know, you may not actually have to look up the coefficients, but if you wanted to do hand calculations to verify the software calculations, then this is how you would do it. So next thing we wanted to talk about was the application comparison. So a model application comparison between 2002 and 2018. So this is the summary of the model application that is presented in 2002 and in 2018. And if you look and compare the two, they are exactly the same. Basically, the steps are the same. It's just to complete the steps and the inner details, or the working details in each of these steps, has changed. So in both editions, you were to determine the arcing current, then determine the arc duration or fault clearing time based on the arcing current. That then gives you the ability to calculate the incident energy, which then allows you to determine the arc flash boundary. And then you need to repeat the first 4 steps again for the reduced arcing current. So like, you know, in 2002 that was the 85% rule. 2018 is the minimum arcing current calculation that you'd have to perform. So once you know that, you then recycle it back into steps, you know, 2, 3, and 4 because you would have that minimum arcing current. So in general, you know, 2000 2018, the outcomes of each of these steps are pretty much the same, but the process in determining those outcomes has changed. So diving into each of these, item 1 through 5, in a little more detail, you can really start to see the differences between the 2 different codes. I haven't put very much equations on here, or really any equations except for a few slides, mainly because the equations are pretty long, and it would extend this presentation quite significantly. But all the equations are actually in the standard, and they tell you step by step what to do. So it's a great way to follow, and there's a summary in the standard to tell you how you go about calculating and how you determine the incident energy. So looking at 2002, basically, step 1 is determine the arcing current, and in 2002 there's 3 things you need to look at. For system voltages less than 1 kV, they say use equation 1. For system voltages greater than 1 kV or equal to 1 kV, use equation 2, and then also calculate 85% of the arcing current that you determine in steps A or B, and that'll be used in step 5. In 2018, you still need to determine the arcing current, but there's a number of things you have to do before that. First off, you need to determine the equipment electrode configuration. So that's your HCB, your HOA, VCB, VCCB, and VOA electrode configurations. And then you need to look at to see if the system voltage is between 600 volts and 15 kV, and if so, use equation 1 for the intermediate arcing current. You then need to use equations 16, 17, and 18 to find the final value of arcing current, which takes into account some of the correction factors. And then step C, if the system voltage is between 208 volts and 600 volts, you still need to use equation 1 for the intermediate arcing current, but instead of using equation 16, 17, 18 for the final value, you use equation 25, which is a little simpler than 16, 17, 18 to find the final value of arcing current. So once the arcing current has been determined, the next step is to determine the arc duration or the fault clearing time. And this is basically a review of the protection settings and maybe reviewing some TCCs or time current curves to determine how long it'll take at the calculated arcing current to clear the arcing current. These steps are very similar, and in 2018 there's an additional section that says see section 6.9.1 for further guidance. So once the arcing current and arc duration or fault clearing time are known, you then need to determine and calculate the incident energy. In 2002, basically there was these 3 steps listed here. Step A was to find the normalized incident energy using equations 4 and 5, and then step B was to take that normalized energy and convert it to a final incident energy by using equation 6. And for voltages that are greater than 15 kV, 1584 2002 edition recommended using the Lee method, which was equation 7. And I won't go into details on the Lee method, but that was kind of how it was done in 2002. In 2018, the next step you need to do is determine the enclosure size correction factor. So this is where your enclosure size really comes into play. Back in when you determine the arcing current, it was the electrode configuration, but now it's the enclosure size because there are different incident energies that are based on the enclosure size. And similar as into the arcing current, the next step is if your system voltage is between 600 volts and 15 kV, it says use equations 3, 4, and 5 to find the intermediate values, and then you follow that up by using equations 19, 20, 21, and the guidance in section 4.9 to find the final incident energy value. But if your system voltage is between 208 and 600 volts, the open circuit voltage, it says use equation 6. So equation 6 is a little simpler, and then guidance for the final incident energy is provided in section 4.10. So if you're doing calculations at a 480 volt system, your incident energy calculation would be a little bit simpler than if you did calculations at a medium voltage system or something above 600 volts. And then there's some other language in the standard that says additional considerations should be evaluated, and some other guidance has been provided in section 6.10. So once the incident energy has been determined, like I said, the next step is to determine the arc flash boundary. And in 2002, the arc flash boundary was determined by a simple equation for different voltage levels. The first one was based on the empirically derived data that was taken that was less than 15 kV, and it says use equation 8. For the Lee method, or voltages that are greater than 15 kV, use equation 9. In 2018, to determine the arc flash boundary, you need to look into section 4.8, which gives you guidance on the enclosure size correction factor. And then, based on that, you would then perform a calculation. If your system voltage was between 600 volts and 15 kV, you would then use equations 7, 8, and 9 to find those intermediate values. And then you would then use equations 22, 23, and 24, and then guidance in section 4.9 to find the final arc flash boundary values. So it's very similar to the incident energy calculations where you need the enclosure size correction factor. And if the system voltage is again between 208 volts and 600 volts, we would use equation 10. Additional guidance is provided in section 4.10 for the final arc flash boundary calculation. And now the final step in completing the incident energy analysis at one particular location would be to repeat steps 1 through 4 that we just discussed for the reduced arcing current. So in 2002, it was just rerun the same calculations with the arcing current reduced at 85% of the calculated value. While in 2018, you would need to use the guidance in section 4.5 for arcing current variation, which is equation 2. So it's no longer, like I said earlier, it's no longer the 85% arcing current value. It is now, you now need to calculate to determine the lower bound of the average RMS arcing current. And that equation is actually shown here in the bottom left by IARC min. And it's, then there's also a variable or correction factor, is the arcing current variation correction factor. So that's all plays into calculating the IARC min. And then that IARC min is then used as an input into the same equations from steps 2, 3, and 4. You wouldn't do step 1 because you've already calculated the arcing current. And now you're going to repeat steps 2, 3, and 4 with the minimum arcing current based on this equation. And if you're looking for examples on calculations, 1584 2018 edition, Annex D, D as in dog, has 2 different examples. There's a 480 volt example, which actually runs through the inputs, and then it goes through each calculation, and then it makes determinations on what the incident energy would be. And then there's also an example in for 4.16 kV or 4160 volts. And that example kind of goes through a medium voltage example as well. So those are some 2 very important calculation examples that allows you to follow the steps that I just kind of covered from steps 1 through 5, and allows you to see what was made, what was included, and where they got the data from. So I encourage everyone, when you're doing these arc flash calculations, to actually run through these example calculations before you do an actual client or customer calculation, just to, if you haven't done it before, to get your feet wet and to understand where everything's coming from. So in closing of this presentation, wanted to kind of go over again the takeaways or the learning points from the very beginning of the presentation. And the overarching one is that the 1584 2018 edition standard has changed significantly from the 2002 edition. While the outcomes and some of the steps are the same, how you go through those steps and how you get those intermediate outcomes have changed significantly. Partly due to the change in the equations, the more accurate equations and more complex based on more available test data and the statistical analysis that was performed on that test data, as well as the need to gather additional information as inputs into the 2018 edition arc flash study versus those inputs were not available in the 2002 arc flash study. So with those takeaways, I'd like to open up the presentation now, or I would like to invite some questions. Before I do that though, I would like to thank Grace for inviting me to give this presentation, and like to thank everyone for attending this presentation. Hopefully it was informative and it kind of gave you some guidance on how to perform these calculations now, and what other additional information you may need to gather to perform these calculations. So with that, thank you very much. You can find my contact information if you just do an internet search for my name and then append that with Exponent. A lot of my emails and telephone numbers and stuff are provided on that website. So thank you, and I'm happy to answer any questions.